My message to young and up-and-coming researchers would be that the most important thing, pursue what your passion is, because that's where you'll do your best work.
To get just how remarkable Manjul Bhargava is, let's start with the Fields Medal. Often called the Nobel Prize of Mathematics, the Fields Medal is awarded only once every 4 years, and only to mathematicians under 40. When Bhargava received the Fields Medal in 2014 at the International Congress of Mathematicians in Seoul, it confirmed what many in the field already knew. He is one of the most important mathematicians of his generation. Bhargava's academic background is impressive. He earned his doctorate at Princeton University, studying with Andrew Wiles, the mathematician famous for proving Fermat's last theorem. As a graduate student, he solved a major 200-year-old problem first posed by Carl Friedrich Gauss, often called the Prince of Mathematicians. He has made significant contributions to the Birch and Swinnerton-Dyer, or BSD, conjecture, one of the 7 Millennium Prize problems, which are 7 of the most difficult and famous unsolved questions in mathematics. Each carries a $1 million reward for the first correct solution to each problem. In 2015, Bhargava and Arul Shankar proved that BSD holds for at least 66% of all elliptic curves.
I think mathematicians do mathematics for reasons that are very similar to those of musicians playing music, or any artist doing their art.
Manjul Bhargava was born on August 8, 1974, in Hamilton, Ontario, Canada, but he grew up primarily on Long Island, New York. His father was an industrial chemist, while his mother, Meera Bhargava, was a mathematics professor at Hofstra University. It was Meera who became his first and most influential teacher, developing a home atmosphere where curiosity was free to roam. Even as a toddler, Bhargava loved numbers. He was full of energy, and his mother found that the best way to keep him occupied was to ask him to add or multiply large numbers in his head. He had his own way of figuring out answers, often moving his fingers as he thought. When his mother tried to understand how he did it, he couldn't really explain. It just came naturally to him. Rather than being satisfied, he would often ask her, "Teach me more math." School lessons soon felt too slow and dull for Bhargava, who learned best by exploring on his own. When he was 8, his mother asked him to help with the oranges before juicing. He started stacking them into triangular pyramids, but instead of just counting the oranges, he wondered whether there was a formula to determine how many were needed for a pyramid of any size. After months of thinking about the problem, he came up with the formula himself. That was a moment that changed how he saw math. "That was an exciting moment for me," Bhargava recalled. "I loved the predictive power of mathematics." For a child like Bhargava, who learned by exploring and doing, school was dull. He found the slow, repetitive lessons boring, so he mostly taught himself. Although his family valued public education and didn't push him to skip grades, they allowed him to miss a lot of school. Bhargava often missed school for months. When classes didn't interest him, he stayed home to read or went with his mother to Hofstra University, where he sat in on her college math lectures. The college students were often surprised and sometimes amused when the 8-year-old once corrected the professor's math. Even though he missed a lot of school, Bhargava stayed socially active. He played tennis and basketball with his classmates from Plain Edge High School, and his friends remember him as a normal kid who never showed off his intelligence. By 9th grade, he had finished all the math and computer science classes his high school offered. He entered and won the first New York State Science Talent Search. Still, his unusual path almost caused problems. In his senior year, a health teacher tried to stop him from graduating because he missed so much school. Luckily, the school leaders disagreed. Bhargava became valedictorian, and the school was proud to send him, someone who wasn't an athlete, to Harvard. Going to Harvard was a turning point for Bhargava. For the first time, he was surrounded by top-level mathematics. Unlike many classmates, he hadn't competed in math Olympiads, but his self-taught background made him just as strong, if not stronger, than those with more traditional training. At Harvard, Bhargava learned from well-known teachers like Percy Diaconis, a former magician. Diaconis showed him the math behind coin flips, card shuffling, and magic tricks, a mix of fun and serious study that suited Bhargava well. During college, Bhargava began moving from simply learning math to creating his own ideas. Bhargava accomplished a lot as an undergraduate. His senior thesis, which built on earlier research, won the Hoops Prize. He also received the 1916 Frank and Brenny Morgan Prize for outstanding undergraduate research. Besides his research, he was a talented teacher, winning the Derek Bock Award for Excellence in Teaching 3 times, a feat no other undergraduate had achieved. During these years, Bhargava thought seriously about becoming a musician, economist, or linguist. But he realized what he liked most in those fields was their connection to math. Somehow, I always came back to math, he noted. He decided that being a mathematician who played music was easier than being a musician who tried to do advanced math. When he graduated summa cum laude and was salutatorian at Harvard's 1996 commencement, the faculty knew he was on his way to becoming a math legend.
So this goes back 4,000 years, and their natural next questions: what if instead of a squared plus b squared equals c squared, I look at a to the fourth plus b to the fourth equals c squared? Well, that was a question that was considered 400 years ago by Fermat.
Princeton became the place where Bhargava's career truly took off. He arrived for graduate studies with a Hertz Fellowship, joining one of the world's most renowned mathematics departments. There, he studied under Andrew Wiles. Andrew Wiles is a legendary figure in mathematics. In the 1990s, he became famous for proving Fermat's last theorem, a problem that had puzzled mathematicians for more than 300 years. Studying with Wiles meant joining a tradition of ambitious research. Bhargava didn't work in exactly the same area as Wiles, but Wiles helped Bhargava develop a sense for what fundamentally matters in mathematics. As a young mathematician, you don't always know what is important, Bhargava said. Professor Wiles had a sense of the most influential or the most important mathematics. With Wiles' guidance, Bhargava developed his own style. Bhargava quickly made a name for himself in the department. After a short time at the Institute for Advanced Study and a return to Harvard, Princeton appointed him to the tenured rank of full professor in 2003. At just 28, he became one of the youngest people to reach that position in the university's history. Bhargava works in number theory. Simply put, number theory is the study of how whole numbers, like 1, 2, 3, and 4, behave and relate to each other. At first glance, number theory seems simple. It asks basic questions. Which numbers are prime? How can numbers be factored? What patterns appear when you add squares or cubes? But this simplicity is misleading. While whole numbers are so basic, the patterns within them are often very hard to uncover. Sometimes, a question a child asks will puzzle top mathematicians for centuries. Number theory is the foundation of modern cryptography. Every time you use a credit card or send a secure message online, algorithms based on prime numbers keep your data safe. In the early 1800s, the legendary mathematician Carl Friedrich Gauss published Disquisitiones Arithmeticae, a landmark book that continues to shape number theory. In it, Gauss explored binary quadratic forms, which are polynomials in 2 variables with squared terms. Gauss wondered how these number patterns could be combined. He found a composition law stating that multiplying 2 quadratic forms yields a 3rd quadratic form. This was a major breakthrough, but his explanation was extremely difficult to follow, taking 20 pages of tough algebra. For 2 centuries, mathematicians used Gauss's law, but they struggled to fully understand it or apply it to more complex equations. Enter Manjul Bhargava, late one night in his dorm room at Princeton. He was playing with a Rubik's Cube, or more specifically, a mathematical variation of it. He wondered what would happen if, instead of coloured stickers, he placed numbers on the cube's 8 corners. By slicing the cube in half along its 3 different axes, he generated 3 pairs of matrices. When he worked out the determinants of these matrices, he found 3 different quadratic forms. Surprisingly, their mathematical signatures all matched. With this simple geometric idea, Bhargava had recreated Gauss's composition law. He didn't just solve an old problem, he changed how people could understand it. Using a simple 2 by 2 by 2 cube, he replaced 20 pages of old algebra with a visual model that even a high school student could hold and explore. Bhargava's cube slicing idea was impressive, but he didn't stop there. He saw that his geometric approach was able to unlock even more. If a 2 by 2 by 2 cube led to Gauss's law, he wondered what would happen if he changed the cube or tried a Rubik's domino. Over the next few years, he found 14 new, higher composition laws. He expanded the theory far beyond squares, exploring more complex forms like binary, cubic, quartic, and quintic structures. Experienced mathematicians were amazed by Bhargava's work. It was highly creative, and Andrew Wiles said it surprised everyone. The term higher composition laws became central to Bhargava's PhD thesis. He introduced a new style of mathematics that was deep but also relied on visual geometric models. As Montreal number theorist Andrew Granville remarked, somehow he extracts ideas that are completely new or are retwisted in a way that changes everything. But it all feels very natural and unforced. It's as if he found the right way to think. When comparing the Fields Medal with the Nobel Prize, many readers naturally assume a Fields Medal is awarded for a major breakthrough, as in the case of the Nobel Prize. But that's not always the case for the Fields Medal. In Bhargava's case, the medal recognized a sweeping body of work that collectively transformed several central questions in number theory. One of his major breakthroughs came in the study of elliptic curves. An elliptic curve is a kind of equation. When you graph it, you get a smooth, curved shape. Elliptic curves are central to modern number theory and cryptography. A big question about them is their rank, which is basically how many rational solutions, those using fractions, an elliptic curve has. For years, mathematicians struggled to solve this for individual curves. Bhargava changed the way people approached this problem. Working with his student Arul Shankar, he used a field called arithmetic statistics. Rather than solving one tough equation at a time, they studied how groups of equations behave as a whole. Using this statistical approach, they made a major discovery. The average rank of all elliptic curves is at most 1.5. They also showed that many of these curves have a rank of exactly 0, so they have very few rational solutions. By looking at the big picture, Bhargava connected his work to the Birch and Swinnerton-Dyer conjecture. Another of Bhargava's best-known contributions involves quadratic forms and the 15 theorem. Bhargava also created the Bhargava factorial. The usual factorial function has been important in math since the 1800s. Bhargava expanded on this idea, showing that factorials can be defined for any set of integers or any ring using a method called orderings. How does Bhargava's mind work? For him, doing mathematics is rarely about sitting at a desk and working through equations. He thinks in a very visual, structural, and hands-on way. His office on the 12th floor of Princeton's fine hall is filled with mathematical toys. Different Rubik's cubes, colourful Zohm tools, puzzles, decks of cards, a 3D Taj Mahal puzzle, and pine cones. He uses these objects to visualize how patterns fit together. He actually spends little time at his desk when thinking deeply. Bhargava likes to do his hardest mathematical work while walking in the woods. Most of the time when I'm doing math, it's going on in my head, he says. It's inspirational being in nature. He describes this way of thinking as practically meditative, a state of deep focus. This way of thinking depends heavily on patience and on letting ideas develop over time. Instead of forcing solutions, he lets ideas grow in his mind. Often I am not thinking about any particular problem at all, he says. I am just thinking wherever it leads. Often The problem being solved emerges only later. The only downside is that if he doesn't quickly write down his insights, he can forget them as fast as they come. He has been strongly influenced by India's heritage, culture, and ancient intellectual traditions. As a child, Bhargava often missed regular school to spend long visits in Jaipur, India, with his grandparents. His grandfather, Purushottam Lal Bhargava, was a respected scholar of ancient Indian history and served as head of the Sanskrit department at the University of Rajasthan. On early morning walks, his grandfather taught him Sanskrit and introduced him to the rhythms of ancient Indian poetry. Through these lessons, Bhargava saw a deep connection between art and mathematics. He learned that ancient scholars like Brahmagupta had created advanced ideas about numbers long before the West did. He also found that the patterns in Sanskrit poetry were very mathematical. He often points out that the Fibonacci sequence, where each number is the sum of the two before it, was described by Indian poets centuries earlier as they worked out rhythmic patterns. He is a skilled tabla player, a traditional Indian drum, and has trained with master teachers like Zakir Hussain and Pandit Prem Prakash Sharma. For Bhargava, music is more than a hobby, it's an important part of how he thinks about math. The tabla player has to figure out how to fill a time cycle, like 8 beats, using different patterns of long and short beats. Bhargava compares knowing these rhythms to a painter knowing their colors. Math tells you what's possible, but art helps you choose what sounds best in the moment. Music also helps him reset his mind. I often use music as a break, and many times I come back to the math later and things have cleared up, he says. People who know him describe him as kind, friendly, and truly humble. His Princeton mentor, Peter Sarnak, praises him not just as a thinker, but as a human being. Sarnak notes that Bhargava fights injustice in his mild-mannered way, going out of his way to fix situations where he sees someone being treated unfairly. Importantly, despite the avalanche of global awards, Sarnak observes that Bhargava is immune to developing a swollen head. He remains highly approachable to students, peers, and the public, carrying his mathematical superstardom incredibly lightly. Harvard's Benedict Gross describes Bhargava's unique charm, saying he lives in a wonderful, ethereal world of music and art. He floats above the normal concerns of daily life. He believes that teaching math through memorization is a mistake that keeps students from seeing its beauty. At Princeton, he creates courses for non-specialists to help fix this problem. He is well known for creating a freshman seminar called The Mathematics of Magic Tricks and Games, and another course, The Magic of Numbers, for humanities students. In these popular classes, Bhargava often starts with a card trick, like the Hummer Shuffle, and asks students to figure out the math behind it. He avoids PowerPoint and prefers writing on blackboards. His dedication to sharing math goes beyond the university. He is very involved with the National Museum of Mathematics in New York, where he was the first distinguished visiting professor for public dissemination of mathematics. He often hosts public events, using interactive magic to show how simple ideas can lead to surprising complexity. Besides the Fields Medal, he won the Sastra Ramanujan Prize in 2005, the Cole Prize in 2008, the Fermat Prize in 2011, and the Infosys Prize in 2012. Popular Science named him one of its brilliant 10, showing his impact beyond math circles. In 2015, the President of India gave him the Padma Bhushan, the country's third highest civilian award. Today, Manjul Bhargava is the Brandon Fradd Professor of Mathematics at Princeton and the Stieltjes Professor of Number Theory at Leiden University in the Netherlands. He also holds adjunct positions at leading Indian institutions, including the Tata Institute of Fundamental Research. His research is still going strong, supported by National Science Foundation grants. He is now studying rank stability in quadratic extensions, the chances of square-free values in polynomials, and important questions in arithmetic statistics and Fourier analysis. His public role has also grown. In early 2026, New York City's Museum of Math named him its first president, a role in which he leads exhibit design, strategy, and public outreach at its new Chelsea location. In March 2026, he led a major public event called First Proof, during which top scientists discussed whether modern AI could perform research-level mathematics. Bhargava keeps his family life private. His respect for all living things, shaped by his childhood in India, led him to become a vegetarian and an environmentalist. He practices Hinduism mainly as a guide for ethical living. Bhargava took a break from Princeton to join the steering committee for India's national education policy. He strongly pushed to end rote memorization in Indian schools and give teachers more freedom to design creative lessons. He wanted all children to experience the joy of discovery, just as he did when he found the formula for a pyramid of oranges.